So far, we've seen LTI systems and that we can input a function and get an output, or that we can give an impulse and then get the impulse response, and then how that impulse has changed. We already know how our input will change if we would give it to our system. Now some other properties that these LTI systems can actually give to us. And one of these properties, well, actually before I go over these properties, let me just rewrite these functions again because they are also very important. If we input an x, then we call its output a y. If we input a step function, then the output is the step response function. And if I input a delta function, then the output is the delta, the impulse response function. Well, two of these properties I've already explained, but I'll explain them again. There's linearity. When a system is linear, that means that if I have a y 1t plus a y of 2t, that this is the same as when I would have input two functions separately, or if I've just put them both through the system at once. Then we have time invariance. When a system is time invariant, it means that changing or shifting through your function after it has gone through the system is the same as shifting your function before it goes through the system. Shifting does not tell you anything about the function. Doesn't change anything if I shift before or afterwards. More properties that we have. One of them is a memoryless system. And when a system is called memoryless, it means that yt is only influenced by x of t. So influence by x of t, meaning that yt is only influenced by x of t, but not any value before this t or after this t. It does not depend on the past or the future, just this point in xt. Then we also have causal systems. If it's causal, it means that y of t is only influenced by x of td, where td is smaller or equal than t. So the past and the present only influence the y of t, nothing of the future. And this can also be seen if your impulse response is 0 for all t smaller than 0. If this is the case, then your system is causal. So every system that is memoryless is also causal, but not every system that is causal is also memoryless. Then we have a stable function, or sometimes also called bibostable, for a bounded input, bounded output. And what that says is that if we take our impulse response, that the absolute value of this should be lower than infinity, meaning that we have a finite piece of our input function that has a surface, is non-zero. After that, it doesn't go onward to infinity, because every function that is non-zero that goes on to infinity is not stable. Then we also have invertible systems. And an invertible system just says if we give our y as an input, the output is our original input back again from another function. Then the system is invertible, or is an invertible of another system. And we have cascades. And cascades we will talk about more as well in the last video. But if we have an input function, it goes into a system, t1. What we get out is, let's say, w of t. And it goes into another system. And this can even go onward forever, but let's just say 2 functions. Then we knew that if we convoluted the input with our impulse response, then we get the output. But actually we can see as if this was one big system. Like this. As if it is one big system. Then its impulse response is given by impulse response of 1 convoluted with the impulse response of the second. Then we know all the changes that have been made into from simple functions into a new function, which gives us h of t of the whole function. And then we just, for our output, we just have to convolute x of t with this new h of t. And that is how cascades work. Now, for every of these functions, I'm going to give you something, a function that does hold and does not hold. So one for linearity is one that I will use actually for each and every one, is a system that just differentiates anything that is put into it, towards t, of course. This is your output. This is what your system does. It just gives the derivative function of whatever you put it into. It is linear because you can just add derivatives onto each other or just put them in derivative at once. Something that is not linear is a function that just creates the logarithm of your input, because a plus b is not the same as log a plus log b. That is multiplication. So for time invariance, which function is correct for this? Well, again, the differentiator, which I will use for every example here. It is memoryless, it is causal, it is stable. And of course invertible, because it has its integrator part. Which function is not time invariant? Well, it's a function that, or a system that actually just multiplies whatever has been put into it. So it stretches over the x-axis. And if it does that, if I go 1 to the right before I convert it, is different than going 1 to the right in the output. This is also not a time invariant system. A system that is not memoryless is a system where we take our input function and just shift the lid a little bit to the left or right. Then I need to know something of my past or present in order to know what the y value will be at this specific time. And the same for causal systems, only then we look at a difference where we shift actually one to the left. So in this case, TD needs to be positive. If TD is positive, then we shift to the left, and then we need to know the future of our function to write down and the function that we have right now. So we could say that like y of t is x of t plus 1. Then we need to know the future for our output. And another function that doesn't use, that isn't stable, or given a function that is not stable. One that is stable is of course again the differentiator. One that is not stable is if we take the sign of our input. Like that. Because a sine function goes on for forever, and its surface from -infinity to infinity is actually infinity. So this system is not stable. And of course, this almost every system is invertible. There may be some functions that are not invertible, so systems that are not invertible. But right now, I cannot think of any or didn't find any so far. So these are some very important properties or some very fun properties about these LTI systems. There are way more properties that you can actually have for your system, because systems can go on much more in detail. But these are the system properties that are important to us, especially the cascades